Hi everyone, this is Peter Jasper and welcome to my YouTube channel. In this video, we will discuss about the comparative study between SN1 and SN2 reactions. So, we will take some terms and some comparisons between SN1 and SN2 reactions in this video. So, the first comparison is branching on alpha carbon. So, what about the branching on alpha carbon in case of SN1 and SN2 reactions? On alpha carbon, if branching increases, alpha carbon branching increases, SN1 reaction rate increases, but SN2 rate reaction decreases. If branching increases, SN1 increases, but SN2 decreases. And what is the alpha carbon? The carbon attached to the functional group is called alpha carbon, and I am taking 4 examples, and we will compare these 4 examples about the reactivity in SN1 and SN2 reactions. So which is the more reactive in SN1 and SN2 and which is less reactive in SN1 and SN2. So first we will compare in terms of SN1 reactions. In SN1 reaction, fourth one is more reactive than third, second and first one. And in SN2 reactions, first one is more reactive than second one, third one and fourth one. And the second comparison is branching on beta carbon. So what happens about the branching on beta carbon? If branching on beta carbon increases, SN1 reaction rate increases and SN2 reaction rate decreases. So here, if branching increases, SN1 increases and SN2 decreases. And what is beta carbon? The second carbon attached to the functional group is called beta carbon, and I am writing 3 examples, and we will compare these 3 examples in terms of SN1 and SN2 reactions. And the reactivity in SN1 reactions are, in SN1, third one is more reactive, and then second one and first one. In SN2 reactions, it is quite opposite, first one, second one and third one. And next comparison is unsaturation on alpha carbon. Simply unsaturation means alkenes, means double bonds and triple bonds. But here in this unsaturation case we will discuss only about double bonds. So at alpha carbon, if unsaturation is present, both SN1 and SN2 rate increases. So why increases? Because halogen lone pair is involved in mesomeric effect. So here halogen lone pairs are involved in mesomeric effect. So both SN1 and SN2 reaction rates increases. And here I will write 2 examples. And in this halogen lone pairs are involved in delocalization with phenyl and with double bonds. And very important point in this is vinyl halides and aryl halides are not involved in nucleophilic substitution reactions. And next comparison is unsaturation on beta carbon. So what happens if unsaturation is present on beta carbon? On beta carbon, if unsaturation is present, both SN1 and SN2 rate increases. So why both SN1 and SN2 rate increases if unsaturation is present on beta carbon? Because delocalization increases SN1 and SN2 reaction rates. So delocalization increases both SN1 and SN2 reactions. And now again I am writing 3 examples and we will compare those 3 examples. Both in case of SN1 and SN2 reactions, their reactivity is same. So SN1 and SN2 reaction rates, third one is more reactive and second one and first one. Next comparison is nature of living nucleophile. So what about nature of living nucleophile? Good living nucleophile or good living group increases the both SN1 and SN2 rate. So if it is a good living nucleophile, then SN1 and SN2 reaction rate increases. So here one important point is weak base is best living group or best living nucleophile. Weak base. In halogens we will compare about their basicity. Here now the nature of incoming nucleophile. So what is the effect of incoming nucleophile on SN1 and SN2 reactions? Strong incoming nucleophile increases the rate of reaction of SN2 reactions. So if it is a strong nucleophile, it increases the rate of SN2 reactions. But in SN2 it increases, and in SN1 the incoming nucleophile does not affect the rate of reaction in SN1 reactions. And now we are taking two examples. Here in these two examples, the second example is more reactive than the first one. So when same donor atom is present, nucleophilicity is directly proportional to the basicity. Just remember this point. Nucleophilicity is directly proportional to the basicity when same donor atom is present. And now group present on alpha carbon. So the group present on alpha carbon also affects the SN1 and SN2 reactions. So here G means the group. If it is an electron releasing group, SN1 reaction rate increases, SN2 rate decreases. If it is an electron withdrawing group, SN1 rate decreases and SN2 rate increases. So electron releasing group means the groups which releases the electrons towards a carbon atom. Electron withdrawing group means which takes or which withdraws the electrons from carbon atom. Next, nature of ring or nature of ring size. Here we are taking three examples: cyclopropane, cyclobutane, cyclopentane. Here I am taking its intermediate state, that is transition state. It is 120 degrees. So nearer to 120 angle is more stable cyclo compound. And if the bond angle deviation decreases, both the SN1 and SN2 reaction rate increases. If bond angle deviation decreases, SN1 and SN2 rate increases. And next one is the isotopic effect. So here deuterium is more reactive in SN2 reactions, but hydrogen is more reactive in SN1 reactions, because in SN1 reactions carbocation stability is important. So here we are considering hyperconjugation concept. That's why SN1 reactions hydrogen is more reactive, in SN2 reactions deuterium is more reactive. Solvent effect. Polar protic solvent increases SN1 rate. If it is a polar protic solvent, SN1 rate of reaction increases, but polar aprotic solvent increases SN2 reaction rate. If it is polar protic, SN1 increases. If it is polar aprotic, SN2 increases. Both are different. And now let's see the example. Here solvent is DMF, and in second example solvent is H2O. Sorry, it is not visible to you. because of some problems. And DMF is polar protic solvent. So because of polar protic, first example is more reactive in SN1 reactions, and the last two comparisons are there. So phase transfer catalyst. Phase transfer catalyst increases the rate of SN2 reaction. So we are taking two examples. In these two examples, the second one example is more reactive than the first one. Second is more reactive than first one because 18 Cron 6 is a phase transfer catalyst. Now ultrasound waves. Ultrasound waves increase nucleophilic substitution reactions. That means both SN1 and SN2 reaction rate increases because of ultrasound waves. So why increases? Because of temperature increases. Temperature increases, so nucleophilic substitution rate of reactions increases.